on. There's a universe in which I could come in. Good morning, everyone. Hope everyone enjoyed the banquet last night. I wanted to remind you, since Ethan just reminded me, since I'd forgotten, that our TASI photo, which is a TASI tradition, will be done this morning after the first lecture. So before we hang out and talk, we'll all go outside together and walk a little of the way back towards where the dorm is, to Farron Field, which is this sort of nice green area that you walk by. It's where we usually take the picture. Then we'll come back and finish our coffee break. So hopefully this morning it will happen. And with that, we're happy to have another lecture from John McGreevy. So take it away, John.
All right, hello. So in the last lecture, I tried to persuade you that you should think of at least some kinds of topological order as spontaneous breaking of discrete higher form symmetries, and that you should think of the reason the photon is massless as a consequence of, again, spontaneous breaking of, in this case, a continuous higher form symmetry. So it's sort of I guess a good analogy to keep in mind is the following picture, that discrete symmetry breaking is to continuous symmetry breaking as, maybe people don't know this notation anymore. It used to be on the SAT. It's an analogy. This thing is to this thing as, I guess here I should draw some mascot for topological order, something like that, as this is to, okay, how do you draw a photon? I don't know, I guess Lagrangian is f squared. Okay, so that's the analogy that we were pursuing, and there's a sort of failure of this analogy that I want to talk about now, which in some senses it means that higher form symmetries are more powerful than ordinary symmetries. Yeah, so this is the question of robustness of higher form symmetries. So in this case, if I explicitly break, yeah.
I just want to make sure that the massless of the photon is the explicit breaking of some higher form.
Spontaneous, yeah.
Is that true of the physical photon or the photon in this U1 Maxwell theory?
Well, okay, good. So the question is whether the photon by which we're seeing each other should be thought of as a Goldstone boson, or whether that's only the case for some sort of abstract Maxwell theory. And I think the answer is yes. Nobody's seen any monopoles, and that means that nobody's seen a magnetic. Well, okay, nobody's seen more than one monopole. That means magnetic field lines don't end, and so there's this higher form symmetry, and indeed, in the Coulomb phase, that symmetry is spontaneously broken because the Wilson loop has a perimeter law, or nearly a perimeter law. So even the real one, I think so. So, but there's an awkward aspect of this, which is there could very well be magnetic monopoles. I mean, if not in the sense of like there's one over there, there could be magnetic monopoles in the sense that the spectrum of our universe could include them, and if we were powerful enough or creative enough or had enough cosmic strings, we could make them, or somebody could make them. And that means that the symmetry that I just said is protecting the mass of the photon, masslessness of the photon, is actually not an exact symmetry, right? If there is the possibility of magnetic monopole in the spectrum, it's exact symmetry. And so in this case, if you explicitly break the symmetry, that means you're tilting the potential, right? You're adding to the Lagrangian some charged operator, and in that case, it's a little hard to draw, but yeah, if you tilt the potential, you'll pick out one particular point on the circle of minima, and the gold lemma will have a mass. So it's a very natural question to ask. Does the existence of even arbitrarily heavy magnetic monopoles mean that the photon should have a mass? Right? There are very good experimental bounds on the mass of the photon from I think the best ones come from like looking at things that are really far away, and. Okay, it might be.
I was reading a paper at some point that they mounted it to be like below 10 to the minus 18 eV.
Well, that's pretty good. 10 to the minus 18 is pretty, EV is pretty small. Yeah, indeed. So there's a lot of photons around, and so there are a lot of constraints on the mass. Okay, but the answer to this question is no. Even the presence of magnetic monopoles doesn't mean that the photon gets a mass. So it's a very funny statement. So higher form symmetries can be emergent, but have exact consequences. And the same, and we've already seen such a consequence in this case. So in this case, we said that the phase diagram of the Tor code, there were some perturbations of the exactly solvable point that we considered, and the phase diagram looked like this. And there's a whole region in the phase diagram where there's topological order. And well, from that point of view, maybe the best way to think about it is, so here's some point in the phase diagram, here's some other point in the phase diagram. These 2 points are in the same phase. So we said that if 2 points are in the same phase, then the ground state of one of them, I don't know, let's call it psi A. So this is A and this is A prime. If there's some finite depth, sort of local unitary circuit that produces the ground state of one of them from the ground state of the other one, then they're in the same phase. So V here is so finite depth, meaning the depth of the circuit doesn't grow with system size, and I'd like it to be at least quasi-local, meaning it doesn't necessarily have to be just like a brick wall of 2 qubit gates, but it could be it could have some tails. And it definitely should be unitary. Well, yeah, maybe it doesn't. It has to be an isometry, at least. Well, I'm only telling you what it does in one vector, so what it does in the rest of the Hilbert space doesn't matter. So if there, okay, I'm about to do something else with this. So let's say it's a unitary. If there's such a relation, like there would be if you could adiabatically deform from here to here, then look what we can do. We can take the string operators, the generators of the spontaneously broken higher form symmetry that live here, the ones we wrote very explicitly in terms of products of x's and products of z's in the Tor code. What did I call them? I called them like things like W. So this is the string operator in theory A, and I can just conjugate it by V and make a string operator that commutes with the Hamiltonian of A prime. The fact that maybe it has to be only quasi-local means that although this thing is exactly a string operator with a single lattice spacing of thickness, this thing might be one problem with the Hagoromo-Chok is you can't use the side of it. Right? Maybe a little. Okay, that's pretty good. Yeah, there we go. It's a little fuzzy, right? Because this thing has. Well, even if it's a finite depth circuit, when you act with a finite depth circuit, when you act with any local circuit, there's a sort of light cone, right, of the influence of a given point. Do you know what I mean? No? Oh, okay. So I didn't get a lot of positive response for that. So let me try to draw a picture. So here's a picture of a circuit, and Alejandra warned me that whenever anybody draws a circuit, she turns her brain off. So sorry. I hope not everyone has that reaction. But so think about, so imagine each of these is a unitary acting on, this is what I meant by a brick wall of 2 cubic gates. This is really a local circuit. Now think about, I have some operator here. So imagine I have an operator acting on a single point. What is the support of the operator that I get by acting on O with the unit with the circuit? So I guess I could conjugate with the circuit. So imagine I reflected this. But so on what, how the operator here is acts on a single point. How big is the operator that I get by acting on it? Well, you can see that there's some range of influence here, which is like a lattice version of a light cone. And as the depth of the circuit grows, the range of influence grows. And so depending on how deep this circuit is, the string operator becomes a little broader. And the way that the topological order is finally destroyed here is that the string operator is no longer localized at all. The length just grows. Okay, so that's a picture of why discrete higher form symmetry can have exact consequences, right? So, and we already saw that, for example, at no finite order of perturbation theory do you split the topological degeneracy, right? You have to go to an order of perturbation theory of order the system size. Okay, so there's a similar story for the photon. There are many points of view on this statement. If you saw the public lecture, I gave the easier arguments using dimensional analysis, but let me give a few slightly more sophisticated arguments, which are maybe a little more convincing. So suppose that there's a magnetic monopole. Suppose that rather than del dot b equals 0, it's del dot b is some density of monopoles, and the monopoles have some mass m. Let's say that they have some dynamics with mass m sub monopole. And there can be electric charges too. Let's think about what happens if we put the theory on a circle. Okay, so let's just put, I guess it's just QED really. QED with monopoles. Put the theory on a circle of radius r. So the key thing is that there's this vector field, whose f is dA. And okay, we're doing compactification, right? I feel like, I used to study string compactification. I get a warm, fuzzy feeling about writing an expression for a vector potential in terms of some lower dimensional vector potential plus some scalar mode. I don't know, let me call it A4 d theta. So let's say theta is the coordinate on the circle. So the vector in 4 dimensions, in 3 plus 1 dimensions, decomposes into a 3D vector, a 3D U1 gauge field. I'm writing really small, sorry. And a scalar, right? This thing is it's the best way to think about it is in terms of the Wilson line around the circle. It's a scalar from the 3D point of view. And okay, so let's think about what happens in 3 dimensions. So this is a 3-dimensional U1 gauge theory with a massless scalar with a compact gauge group, right? It's important that the gauge group is compact. And very famously, Polyakov did this calculation that shows that this theory confines. It confines because of instantons, which they're point-like events which create magnetic flux. And the solution for the instanton is just the magnetic monopole, the Euclidean magnetic monopole in 3 dimensions. And the good way to think about it is to introduce a scalar field, which is dual of this 3D gauge field. And Polyakov showed that monopole instantons, let's just call it V sub p for Polyakov, monopole instantons produce a potential for this scalar field, which is like cosine sigma times the classical, e to the minus classical action of the monopoles. So what's the classical action of the monopoles? Well, so this monopole instanton, it's a Euclidean monopole in 3 dimensions, and it comes precisely from the 4D particle, the 4D magnetic monopole, winding its world line around the circle on which we compactified the theory. So what's the action for a configuration which is a particle of mass capital M sub monopole wrapping around a circle of radius r? Right, it just has some rest mass. So the action is just the mass of the monopole times the radius r. And now there's, okay, let's just compute the whole potential. There's another thing that can happen, which is we said that there could also be electric charges. And so from the 3D point of view, those electric charges can wind around the circle. And that's the only thing that breaks this shift symmetry of this Wilson line. And so there's another term here, which is cosine of, I don't know, let's call it sigma twiddle. Or maybe I should call it, let's just call it sigma twiddle, of e to the minus the mass of the electron times the radius r. So these two, as you can see, these two terms are related by some kind of electromagnetic duality, which it's just electromagnetic duality. And so you see both of the polarizations of the photon get a mass, right? So that, in 4 dimensions, there's 2 polarizations of the photon. When you put it on a circle, there's still 2, but now they have rather different status. But they both get a mass from charged excitations winding around this circle. And okay, but now there's a very important feature of this potential. So you see that sigma gets a mass. If you expand the cosine around 0, you get a mass, which is this, mass squared, which is this, and similarly, you get a mass squared, which is this. And something that you'll notice about both of these masses is that when you take r to infinity, they go to 0. That's the whole point. So in the thermodynamic limit, the photon is massless. So this exponential splitting, this exponential mass for these particles in 3 dimensions, it's the same phenomenon as the fact that the generated ground states of the toric code, when you put it on a circle of finite radius, has an exponential splitting. It's the same kind of exponential. Okay. Another way to think about the calculation that we just discussed is, this theory is Lorentz invariant. I was describing this circle here as a spatial circle, but we could also think about it as the Euclidean time direction, in which case this describes the theory at finite temperature. And so you can see that at finite temperature, there's no massless excitation. And that's related to the following rather awkward fact by this analogy, which is that the phase, so there's a good reason that I put the word quantum in the title of my lectures, which is that unfortunately, all of the topologically ordered states that we know in 3 + 1 dimensions or fewer have the very annoying property that they're only distinct from each other at 0 temperature. At any finite temperature, they're adiabatically connected to the trivial phase. It's really a kind of embarrassing and horrible admission, especially because any experiment is done at finite temperature. The reason for this is actually very simple. It's that all of the topological orders that we know in 3 + 1 dimensions or fewer have the property that they have. Okay, that statement's not true. The topological orders that I talked about have the property that they have particle excitations. They have excitations that, although they're not created by a local operator, the excitation is localized to a point. And that means that at any finite temperature, there's some non-zero density of these anions, right? It's Boltzmann suppressed. It's like e to the minus beta times the mass of the anion, but it's a non-zero density. So there's just like a small number of anions everywhere, and the key thing is that the topological ordered ground states, the difference between them, is the action of the operator that transports the anions, right? So this means that at any finite temperature, there's all these anions around. Here, let's draw a picture. Here, there's this gas of anions. So here's 2 anions. Here's 2 anions. There's some density of them, and they can wander around, right? They have a kinetic term, and if they happen, if they happen to wander around one of the non-trivial cycles of the surface that they're living on, it's exactly the action of these operators that makes the vacuum. So at any finite density, there's really no way to tell which of the states you're in, because they differ by these line operators that are present. So you can see that there's a way around this. Oh yeah, so there's a way around this, which is if you had a theory where the excitations, instead of living at points, were higher dimensional. So if instead of particle-like topological excitations, the excitations were, say, strings, and it's a little harder to draw, but you could imagine a kind of topological order where the operators that mix the vacua are associated with, say, 2 cycles of space-time, right? The action of some string, so some string world sheet on a 2 cycle. In that case, that's a 2 cycle. You can think of it as the path of a string winding around, some other direction. And in that case, at finite temperature, the density of strings. Yeah, maybe I should write an equation. Yeah. So with particles, there's some density of anyons, which goes like e to the minus beta, e to the minus the mass of the anyons over t. And the key point is that m goes like L to the 0. But with strings, if we have instead string excitations, then the density of strings, let's say the density of strings that wind around some cycle is e to the minus tension times L. Oh, I shouldn't. Tension times L divided by t, where L is the size of the cycle, which, let's assume that in the thermodynamic limit we scale up the space uniformly, so all of the lengths grow. And so you see this goes to 0 as L in the thermodynamic limit. So the density of such string excitations is just 0. And so topological order without particle excitations has a chance of surviving at finite temperature. And it's actually it's easy to construct an example of such a topological order. So we said that the Torah code, you could generalize it to the case where instead of living on the links, we put the qubits on the plaquettes or something like that, put them on the P cells. And the only problem is duality. It's really annoying. So in 3 spatial dimensions, if I put the degrees of freedom of the Torah code on the 2 cells, this model is actually just dual to the usual Torah code with the degrees of freedom on the 1 cells, on the dual lattice. So there's strings again. But in 4 spatial dimensions, if you put the degrees of freedom on the 2 cells, it's actually self-dual. It's dual to another theory where the degrees of freedom live on the 2 cells, and this is what happens. So the 4D 2-form Torah code has a topological order that survives at finite temperature. And similarly, if we have a 4D U1 2-form gauge theory, it stays massless even at finite temperature. And that's because this thing has it has a 2-form symmetry. It spontaneously breaks a 2-form symmetry. 4, oh yeah, good, right. Thank you. I broke my rule. I really try very hard to always write the number of space dimensions plus 1, but thank you. Indeed. So it's really, it's hard to fit it in your laboratory. Though not for lack of trying. There's lots of good ideas about trying to sort of squeeze this kind of thing into 3 dimensions. And so a 2-form symmetry has the interesting thing is that when you put it on a circle, there's still a 1-form symmetry. And so when you put it at a finite temperature, there's still a 1-form symmetry that survives. But if you both put it on a circle and put it at finite temperature, then it goes away. Yeah. Okay. So I think that's what I wanted to say about robustness. And so this is it's a slightly awkward thing for purposes of using higher form symmetries as a sort of Landau paradigm, because it means that in the usual Landau paradigm, you just have to think about the exact symmetries of the microscopic Hamiltonian and which of them are broken. But here you have to worry that you're studying some random spin system, which maybe doesn't have any symmetries at all, but it could emerge some higher form symmetries and then spontaneously break them, and in which case that could label the phase of matter. So it's a small awkwardness, and it's also, I guess, the reason that they weren't discovered earlier. Okay. Good. Okay, so now I want to return to this table of what is a symmetry. What's a symmetry? So we made a list. We said it's a collection of operators that commute with the Hamiltonian. They should be supported on codimension 1. Well, okay, we already got rid of that one, so let's not even write it. We said that they should be fully topological. You'd think I'd be able to spell this word by now. And they should form a group, represent a group. Okay, so let's get rid of this one. So the picture you should have in mind is, so I'm drawing a lattice. It actually is not so important. Well, sometimes, okay. I'm drawing a lattice. Suppose we have a symmetry operator supported here. So this is sigma, and okay, this is a good opportunity to use color. So there's one symmetry operator here, and another symmetry operator here, just in different places. These two curves are homologous, but you could imagine a situation where u of sigma is just not equal to u of sigma prime, right? Meaning that but nevertheless they're conserved, and that means that it's actually a stronger constraint, right? It means that there's an independent symmetry acting here from the symmetry acting here. And so this is called a subsystem symmetry. And an immediate consequence of it is that if I have a charge, suppose I have an excitation that's charged under, like say a particle that's charged under the symmetry that acts on sigma prime, it can't leave, right? Because if it left, the amount of charge on this slice would change, and it wouldn't be the amount of charge wouldn't be a conserved quantity. So it means, so this kind of symmetry, I mean, I've been intentionally very vague about exactly what it is, but this kind of symmetry automatically means that there are excitations whose mobility is restricted, right? Excitations which can't move in some direction. Okay. To get some idea about the kinds of phases that arise this way, maybe let me focus on a maybe not representative example, but it's an example that's at least easy to explain given what we've already talked about. Yeah, I guess right. So yeah, I guess I should say such an excitation is usually called a fracton. Maybe fracton is sometimes reserved for an excitation that can't move in any direction, but maybe it's better to use the more general definition. Yeah. It could. Oh, sorry. Yeah, the question was, does the system have translation symmetry? And yeah, I don't think I need to make any demand about that. It could or it could not. Would you like it to? You could do it, but it's a different operator, right? So if there's translation symmetry, it means that necessarily there's an operator here. If there's an operator here, there's an operator here, right? That are related by translations. But it doesn't mean that they're the same operator. It doesn't mean that correlation functions with one of them inserted is the same as correlation functions with the other one inserted. Right? This is a very familiar thing, right? Like if I create a particle here, it's a different operator than if I create a particle here, right? Because the particle it creates is in a different place. It creates a different state. The confusing thing here, the new ingredient, is that these operators are also conserved. They also commute with the Hamiltonian. That's the only new ingredient. Yeah. Okay. Good. So yeah, let me give an example just to sort of focus the discussion. Here's yeah, I guess to paraphrase Shuhang, a stupid example. Yeah, here's a stupid example, which is take a stack of interesting states in 2 + 1 dimensions. So let's suppose each of these is, I don't know, say a Laughlin nu equals a third state. Let me be, okay, I'll be more general, 1/k. So each of these is a fractional quantum Hall state. Each of the layers has topological order. But I just put them on top of each other, right? I just took a pile of quantum Hall states and put them, yeah, just arranged them in these layers. Okay, so let's call this the z direction. So this is a fracton phase. It's a fracton phase because, well, each of these layers has some emergent higher form symmetry, the one we talked about generated by the loop operators, the Wilson lines of the Chern-Simons gauge theory. And they're independently conserved, right? The anyons of this layer are completely stuck to this layer. They can't ever get out, right? They only live in this universe. Okay, so I hope you agree that that's a stupid example. One property that you can see from this example is that the ground state degeneracy on a torus, let's call it a T3, if I periodically identify in this direction, it has a slightly annoying property, which is that I have to independently pick a ground state for each of the layers. Right? Suppose it's a torus in this direction. So imagine each of these squares is actually a torus. But then, and it's a circle in this direction. I have to independently pick a ground state for each of these layers. And so it's, what is it? So for each of them, it's K. And then I have to pick L of them, right? So the log of the ground state degeneracy grows linearly with the number of layers, which, it seems like a crazy thing, right? It seems like a crazy thing. OK, but so let's write an effective field theory for it. It's a sum over Z. Z is this direction of, in each layer, there's a Chern-Simons gauge field, right? Maybe let's call it I. Let's call it I. So let's say this is Z equals I times A, where A is some lattice spacing. So AI wedge dAI. Right? Just a bunch of layers of fractional quantum Hall. So now you can't stop me from generalizing this. So this is the wiggly arrow of generalization. To instead something that looks like this. Pick an integer matrix. So this is exactly the kind of Lagrangian that I wrote for more general abelian quantum Hall phases. The only difference is that now I'm interpreting this I and J label as deconstructing this extra dimension. I used a particle physics word. Yeah. And so, for example, we could choose K just to focus the mind. We could think about K to be. I guess it's kind of nice if it's quasi-diagonal. We could think about something like this. And that's what I mean by quasi-diagonal. So it's, so in this case, K was just exactly diagonal with K's on the diagonal. And here I just allow one off the diagonal. And I guess, if we wanted to be, like here, we could add a Maxwell term. Here, too, we can add a Maxwell term for each of the gauge fields. And see what happens, and we can compute the spectrum of this theory, right? It's a Gaussian Lagrangian. We can solve the equations of motion, figure out what happens. And it turns out that it actually depends a bit on this. It depends on the K matrix. It depends, for example, on this choice of n. For some values of n, it's actually gapless. It's a pretty interesting gapless phase. But for other values of n, it's gapped. There's an energy gap. And so this describes a gap phase of matter where, well, it's a bit like this one. And you can calculate the ground state degeneracy on a torus. And, well, it's not exactly K to the L anymore. Let me write it this way. So the log of the ground state degeneracy, it goes like L. So, and what I mean by that is it actually depends in detail on the value of L. As you vary L, so this is just the determinant of this matrix, basically. Right, the log of the determinant of this matrix, and it involves various number theoretic properties, but there's an envelope as a function of system size, which goes like L, just like here. But nevertheless, so this is a non-trivial class of fracton phases, which share some of the pathologies of this stupid example, but clearly is a true three-dimensional state of matter. You might worry that, well, I just wrote down this effective Lagrangian. How do I know that it comes from some microscopic lattice model? Actually, I'm not sure if anybody here would ask that question. I don't know. But I assure you that actually there is a pretty reasonable lattice model from which it emerges. Yeah.
But if H is 2, it's going to be gapless.
Sorry, is H this letter? I was trying to write an N, but you're exactly right. In the case when it's 2, it's gapless. That's right. But if it's 3, it's not. If it's 3, there's a gap.
What if it's 1 or 0?
So indeed, we can ask for each integer what happens. This is an interesting exercise, and sometimes it's a little crazy. But yeah, I guess how to say, there's a I guess Xie Chen is the person who's pursued this direction the most vigorously, and she has a more recent paper than the one we wrote together, where she explores these things in a bit more extensively. than I have. But my point was to provide an example, right? An easier to explain example of a gap Fraton phase. And when n is 3, it's such an example. And it has a number of crazy other properties. So here we said that the anions were completely localized in each of the layers. The quasi-particles of this theory, they have several funny properties. One is that they're not actually localized to exactly localized to any given layer. Rather, they have some kind of tails. And they have braiding statistics with each other, which in the thermodynamic limit approach irrational numbers, which is not something that you can ever get from an ordinary 2 plus 1D topological phase. And moreover, the braiding is not ultra-local in this dimension. So you can braid non-trivially a particle here with a particle here. So okay, yeah, my main point is that it's pretty crazy. And okay, so that's it's an example of a gap Fraton phase. So why should you care about Fraton phases? I think there are at least 3 good reasons that I know. One is that they provide an enormous class of extremely dramatic exceptions to the long-standing lore that if you have a gap phase of matter, it's described at low energies by a topological field theory. Right, so you can see that there's no way this can be a topological, 3-dimensional topological field theory because it manifestly depends on the size of the system. Right, it knows about the geometry. And so yeah, so it's just not true, at least in 3 dimensions or higher, that the low energy theory of a gap phase is always described by a topological field theory. A second reason is the bad news that I was giving over here, this bad news. So, in fact, one of the ways in which this possibility of fractals was discovered by Zhang-Wan Ha was in a search for models of topological order in 3 dimensions that don't have particle excitations, that don't have where the ground state degeneracy is not produced by string operators. And he did some exhaustive search of a certain class of solvable Hamiltonians, which produced 17 interesting models, of which, some of which are extremely interesting, but actually so far, while they don't have string operators, they still fail to produce distinct phases at finite temperature. So that's still an open question, but it's a motivation for studying more general kinds of topological order. And then a third reason, which is definitely not the last reason, is that they really problematize even the notion of what is a phase of matter. Right? So a phase of matter, I said, is something that you define in the thermodynamic limit. Right? Even to say whether it's gapped or not requires asking about the spectrum of the Hamiltonian in the thermodynamic limit, whether there's a gap or not. So do these theories have a thermodynamic limit? I mean, the ground state degeneracy depends on the size of the system. Right? So it's really not clear even what we mean by the thermodynamic limit in such systems, despite the fact that, maybe I didn't emphasize this here, despite the fact that they can arise from pretty ordinary looking lattice models. Right? So that, I guess if I had more time, I would write down a very simple looking lattice model that nevertheless emerges such a phase. And so people have various ideas about how to generalize the equivalence relation that we put on quantum phases. So I said that in addition to being able to adiabatically vary the parameters in the Hamiltonian in our equivalence relation that says what's a phase, we also said that we could add in decoupled bits and include them in the system and then entangle them by adiabatic evolution. Well, Xie Chen and collaborators have made the interesting suggestion that for classifying Fraton phases, we should maybe allow ourselves to add in layers of 2D topological order by analogy with decoupled bits, and regard those as sort of trivial free resource that we can include. And so if we allow ourselves to do that, then this state is trivial, and this one is a little more interesting. But anyway, I think just raising that point is a valuable and an interesting thing. Okay, so there's a lot more to say about symmetries which are not fully topological, but maybe I won't say anymore. Yeah, please.
I have a question about interpreting L as actually geometric, because at least in the stupid example, it's really just like pi0 of the geometry. So it's really like a topological bit of data.
That's right. So the question is whether we should really think about L as like geometric size of some dimension, because in this example, there's really no information in this example about where the things are. That's right. So at low energies, there's no notion of where these layers are, and I guess my answer to that is just that in this example, there is a little bit more information. There is a notion of a nearest neighbor relationship, and so yes.
Minus 2 is going to be log of G is going to be like log L.
Well, if n is 2, like I said, it's gapless, right? Like you said, it's
right,
gapless.
It's totally geometric data, not topological.
That's right. So yeah, indeed. So whatever n is, right? There's a notion of this site is next to this site. So there is information about where things are, and I guess maybe just to raise the stakes a little bit, it's interesting to note that actually this sort of idea of layering quantum Hall systems is something that people can actually do. Like in semiconductor junctions, I mean, all the time people study like 2 layers, maybe 3, but so there's actually the possibility of realizing this kind of phase in experiments where the things really are layers in space. Yeah, so there's short distance information that does say that that it's actually an extra dimension. Yeah. Okay. Fair question. Okay. Yes, please.
Experimentalists make more than one foliation.
Okay. The question is whether the experimenters can foliate space in more than one direction. I don't think so, but to be fair to the experimentalists, I can't either. So actually, an interesting open question is to find an analog of these kinds of constructions, which is isotropic, where it's foliated not just in one dimension, but in more than one. I don't know how to do that. Yeah, so. Yeah, I think so. Yeah, at the least by making a series of devices where the separation changes, but perhaps by more clever mechanisms also. Yeah. So the question was about varying the tunneling between the layers. Okay, so finally, okay, let's put this back for a second. Finally, we can ask about crossing this out, and Shuheng has been giving a series of beautiful lectures on that subject, so I won't say too much. But maybe I'll just say that non-invertible symmetries. Really, the only thing I want to say about it is we saw that. Well, okay. So sorry. Yeah. So imagine you have topological operators, which when you multiply them, instead of forming a group, instead of producing a third one, you produce some sum of them. So there's not a unique third one, a unique product. So we saw that in the case of abelian topological order, the symmetry operators were just the operators that transport the anyons around, that transport the abelian anyons around. And so we need such a generalization to describe topological order with non-abelian anyons as spontaneous symmetry breaking. So yeah, so that's really the only thing I want to say. So this is what we need in order to describe non-abelian, let's just say non-abelions as spontaneous symmetry breaking. And the key ingredient there is that, well, one key ingredient is that they can split and join. So yeah, maybe I'll write it this way. So if this can happen, it means we can also do this. We can also make junctions between the things, and the outcome of the third one is not certain, and that means that when we braid, okay, as you guys have heard already enough, it means that when we braid these guys, there's actually a whole Hilbert space, a whole degenerate Hilbert space on which to act, and so braiding is not just a phase, but some unitary matrix. Okay, so yeah, sorry to be to give only such a high-level statement, but I think maybe I don't have more to say about it. Okay, so let's return to the big question of the generalized Landau paradigm. So one thing that's missing so far in our conquest of the world is, at least in the discussion of the conquest of the world, is topological phases without topological order. So yeah, there's this nice notion of a symmetry-protected topological phase. No, symmetry-protected topological phase, not stone temple pilots. Okay, which is the following thing. Suppose I have a Hilbert space with some symmetry acting on it. I can, so previously we drew these big scary pictures of the space of all Hamiltonians. And there was this wall of gaplessness. I don't know, let's draw it like that. No, there's some wall of gaplessness. More generally, wall of phase transitions. But we can, okay. If we have a symmetry, we can restrict our consideration to a subspace of Hamiltonians which preserve the symmetry. So, I shouldn't have drawn the wall of gaplessness first. Let's see, let me try. So suppose here is the space of G-symmetric Hamiltonians. Here, you know what? Let me be more creative. Suppose this is probably some non-generic situation, but suppose it's like that. Yeah, suppose that's the space of G-symmetric Hamiltonians. So
What does that say again next to the R?
next to the wall of gaplessness. Yeah, sorry, I feel like I've talked about the wall of gaplessness already too much, so I was embarrassed to write it again. Yeah, the wall that separates different phases from each other. Okay, so I've just drawn some example picture, but one thing you can see is that, so here's a point on the wall of gaplessness. You can see that if I restrict myself to symmetric Hamiltonians, this and this are a different phase, right? Because they're separated by this point through which you can't go while adiabatically deforming. And so this is, we can call this SPT1 and this SPT2. So they're different phases of G-symmetric Hamiltonians, but as you can see, if I allow myself to wander off into the larger world of all Hamiltonians, I can adiabatically connect them. So that's the notion of an SPT. So you see already, even in the definition of SPT, there's this notion of symmetry. Okay, so how can we understand different ones? How this one is different from this one? And well, the answer to this is anomalies, right? So I guess you've already had quite a lot of discussion of anomalies. So maybe, well, let me say it this way. A symptom of an anomaly. No, okay, I guess I don't need to say that right now. Here, let me just say it this way. We can couple the system to background gauge fields. So suppose we're speaking about SPTs for symmetry G. We can couple the system to background gauge fields for G. I don't know, let me call them curly A. And we can ask, how does this transform? Oh, okay, sorry. Yeah, sorry, let me back up a second. Well, okay, so I guess I did mention this already, that a way to distinguish these things from each other is by what they do on a space with boundary. All right, so we can ask about the interface between the SPT, or SPT1 and SPT, or for example, SPT and vacuum. And the idea is that something interesting has to happen here. And the answer is, that the interesting thing is that this thing is anomalous. So the thing in between has some G anomaly. Meaning that the partition function for just the edge theory, coupled to background fields, if I somehow studied some low energy field theory of just the edge theory as a functional of background fields, it picks up some non-trivial phase under a gauge transformation of the background fields. And the whole idea is that that anomaly can be used as a label on the SPT. The anomaly of the edge theory is a label on the SPT. Okay, so so this is a additional ingredient which Landau didn't talk about, but which we need to accommodate such things. Okay, did I get to the end? Oh, okay. One more comment while I'm talking about anomalies. Maybe I'll say it here. Higher form symmetries can be anomalous, and at least in the examples that I've talked about, it has a very simple interpretation. Actually, we already saw, in fact, in all of the examples I wrote down, there was some anomaly or mixed anomaly of the higher form symmetries. What did it mean? Well, I claim that it's just the statistics of the anions, right? So it's equal to the non-trivial statistics of the topological excitations. So one way to think about it is that a symptom of an anomaly is an obstruction to gauging the symmetry. And what does it mean to gauge one of these higher form symmetries? Let's talk about a case where the higher form symmetry operators are the world lines of the anions. Gauging the symmetry means summing over background fields, right? Coupling to background fields and making those background fields dynamical. In the case where it's a discrete symmetry, the background fields are just insertions of the symmetry operators. And summing over those insertions of the symmetry operators means that we sum over all possible anion world lines. So that's, so gauging this higher form symmetry equals, well, okay, the name for it is anion condensation. And it's not such a bad name because, so when we do this, when we sum over all possible anion world lines, and here I guess I'm using anion to mean any kind of topological excitation of any dimension, where, it means that in the ground state, there's an indefinite number of that type of anions. And so the operator that creates the anions is condensed, and that has an expectation value. Okay, so but what does it mean to condense a particle? It means that the wave function for the particle is 1, right? And that's a bosonic wave function, right? This is something that we can only do for bosons. We can only condense bosons. It's a sad fact of life. Yeah. Someday we'll figure out how to do something else, but we only know how to condense bosons. We can only condense bosons. And so any kind of non-trivial self-statistics of an anion is an obstruction to doing this procedure. And if we have mutual statistics of two anions, that's a mixed anomaly, right? That means that the symmetry generated by this world line and the symmetry generated by this world line have some mixed anomaly. Okay, so yes, please.
So this notion of condensing, this is different than like adding a term to my Hamiltonian, like cranking it up and going to some like trivial product state.
Well, that's an extreme example. Yeah, the question was, is this story about condensing anions the same as if I have some lattice Hamiltonian, I add a term to the Hamiltonian that encourages the particles to be there and crank up the coefficient, like, for example, I add to the toric mode Hamiltonian the sum of x's, right, with some big coefficient, right? That clearly creates a product state. That's an example of it. Yeah, it's an extreme example.
But when I gauge something, I get a new theory that has new symmetries. But this is me adding a term to my Hamiltonian. I don't get a new theory. I don't get symmetries.
So I claim that it's a different route to the same result. So here you're doing it in the same way that we can describe a gauge theory by adding a term to the Hamiltonian that imposes Gauss's law at low energies. That's what you're doing. You're adding a term to the Hamiltonian that at low energies gives the theory where that symmetry is gauged. Yeah, so I claim it's a different route to the same thing. But in this case, the end result is a very boring state, right? It happens that when you gauge this particular symmetry, you get a trivial state. Yeah. Okay, good. So I've gotten to about everything I want to say about generalized Landau paradigm, and maybe I'll conclude with an exercise The exercise is think of phases of matter that we didn't talk about and try to figure out how to understand them in terms of symmetry. So if you want, we could do it now, right? If you think of one, you could ask me about it, and we'll try to figure out how to interpret in terms of symmetry. To get you started, maybe I'll make a list of ones that I'm not going to talk about, but that you can think about. A conductor. That's a good one to think about. Amorphous solid is a good one that Roman and Dashwan asked me about already. And another good one is invertible phases. So this is like an SBT in the sense that it's something that, well, it's a phase of matter where if you put there's no topological order. If you put another one on top of it, you can get rid of it. But it doesn't necessarily have any symmetry. An example is the integer quantum Hall state. I should have given an example here. So an example here is just suppose we have G is U1 symmetry. Then an example of an SBT is integer quantum Hall. Just write down the Lagrangian for transimus theory that we wrote before. And set k equal to 1. So the number of ground states on the torus is k. It's just 1. And so we could regard this as an SBT for the U1 symmetry, where the U1 symmetry is star dA. The current is star dA. And that's totally true. There's this chiral edge theory that we saw. That's the interesting thing that happens at the boundary. But then the awkward fact is that if I break this symmetry, you actually still can't destroy it. And so, so this is the exercise. And I'm sure there are many more that I'm not thinking of. Questions? Yeah?
Are there any sort of weird structural aspects of any of those phases that are sort of crying out for explanation?
Okay, the question was whether there are weird structural aspects of these phases that are crying out for explanation, for like a symmetry-based explanation. And well, I think, one answer is the following. I said that gaplessness is something that requires explanation, right? Gaplessness, especially in a phase. And, the Landau Fermi liquid is the most gapless thing that we know about, right? There's a whole Fermi surface worth of gapless degrees of freedom. And historically, we think of its stability as just a consequence of the Fermi surface is like too big to fail. It's the size of the Fermi surface that protects it from going away. But maybe I should say, I think the answer to this question is recently people in particular, Senthil and Dominic Ellis and Ryan Thorngren, have been studying the symmetry structure of theories with a Fermi surface, or a subclass of theories with a Fermi surface, in terms of loop groups. We're thinking of the symmetry as at each point on the Fermi surface, there's a charge conservation, that the number of particles at each point on the Fermi surface is independently conserved. And this is a huge emergent symmetry, which has various anomalies associated with the filling, and perhaps it can be regarded as protecting the gaplessness of the Fermi liquid in the same sense as emergent symmetries, emergent higher form symmetries protect the gaplessness of the photon. So I think there should be some such explanation. Yeah. Okay. So now a question that has come up many times in my lectures so far, I guess as a result of a sort of obvious bias that I'm failing to hide, is in what sense does a single wave function know, like, what phase it's in, whether it's gapped, all this stuff, right? I talked about a gapped state as a property of a state rather than a property of a Hamiltonian until I think Oliver was kind enough to correct me and say that I needed to mention the Hamiltonian somewhere. But I claim that I didn't. I actually didn't need to say anything about the Hamiltonian. And so here's so let me call it the principle of entanglement bootstrap. And put it in a box. It's the statement that all universal properties and of course this statement is begging the question of what is all universal properties, of a state of matter are encoded in a single wave function. Are encoded in not only a single wave function, in the reduced density matrix of a ball, of a single wave function, of a representative, of any representative wave function. Okay, so it's a bold claim. And so for the rest of what I want to say, I want to talk about why I think this is some reasons why I think it's true, and some really striking consequences of assuming it as a principle. Okay, so let's call it entanglement bootstrap principle. Okay, so why do I think it's true? So let me give a list of evidence. Yeah, so a list of evidence for this statement. The first piece of evidence is a ground state, a single wave function, knows whether it's gapped or gapless. And here's why. Using that wave function, we can compute correlation functions of local operators, equal time correlation functions. And we can think about, so psi knows if there's a gap. So without any information about the Hamiltonian, we can still answer the question because we can compute equal time correlation functions of local operators as a function of their separation. And if it's gapped, they'll decay exponentially. This is the kind of statement that I'm sure, somewhere there's a mathematical physicist who's grinding his or her teeth from my saying this glibly, but it's a statement for which there's an enormous amount of evidence, right? It's something that it's just true. It's like a fact, like ADS-CFT. But we don't, I at least don't know how to prove it. I think probably there's more evidence for this than for ADS-CFT. Yeah. Okay. So this implies gap, and it's the kind of thing that somebody should prove. There's a story about Kitaev giving a colloquium once. I think it was at Santa Barbara, where he gave this beautiful talk. I think it was when he was thinking about invertible phases, classification of invertible phases, and at the end of it, maybe it was like a high school student or something, maybe an undergrad, asked him, well, if there's a gap, does that mean that the correlations are short-ranged? And it just like he froze and just like thought very deeply about this for like 10 minutes without saying anything. And then like I think after that 10 minutes he said something like, I don't know. Yeah. So at that level I don't, I also definitely don't know, but yeah, it's true. Okay. So whereas if the gap closes, the correlation length goes to infinity, and we get some power law correlations. Okay. So that's the sort of 0th order point that it knows whether it's gapped or not. Now we can talk about some more refined things. So let's think about, suppose it's the ground state of a CFT. Let's say a 1 + 1D CFT for now. Then I think probably all of you know, and some of you believe in its existence, that the entanglement entropy of an interval of length L is C/6 log L over some cutoff. Was my statement a fair characterization of the situation? How many of you believe in the existence of this quantity? Okay, I see a few people not raising their hands. Well, okay. Yeah, that's interesting. Well, okay, so I'm going to say lots of things about field theory in what follows. But if you like, the way you can think about the use of field theory is the way people used to think about it in the 1960s. So I think I learned this from the book by Sidney Coleman, whose title was taken from the name of the summer school. Which there's a story that in the 60s, like Gell-Mann and I think it was Gell-Mann and Weinberg, they would like secretly in their office do calculations using quantum field theory, and then when they wrote a paper, they would translate it into the language of current algebra, which people believed existed, but nobody believed that quantum field theory existed. And so Gell-Mann I think compared it to he had this very disgusting analogy involving killing a bird and killing a baby cow and then cooking them together and then throwing one of them away. Right? Something about, yeah. Oh, it's ham. I thought it was veal and pheasant. No, I remember veal was involved because it makes it more offensive. Okay, yeah, and anyway, so quantum field theory was like the one that you throw away. Yeah, so if you want to be like the high energy physicists of the 1960s, you can think of it that way, right? We're going to use quantum field theory because it works, and then you can throw it away at the end because in the end the things I'll say will actually be true on the lattice. Okay, maybe that's not quite as good. But free field theory exists. I think probably everybody even then would agree that free field theory exists. Okay, Tom did this. Yeah. Indeed. The advisability of that is something we could question, yeah. Okay. All right, so yeah, this is the case. And so one thing you can see from this form, oh yeah. Okay, great. So one thing you can see from this formula is, so this entanglement entropy is the von Neumann entropy of this thing, the von Neumann entropy of the reduced density matrix of a single interval. Yeah, so this is, let me just remind you, this is minus trace log rho log rho, where rho is the reduced density matrix of a single interval. And look here, it's the central charge, right? A universal quantity characterizing the CFT that we can extract just knowing this density matrix. We can extract the central charge. A similar thing happens in d bigger than 1 plus 1. That the entanglement entropy of a round ball in this case, now the geometry actually matters, of a round ball. There's exactly where it appears depends on the number of dimensions, but nevertheless it computes the F coefficient or the A coefficient, the analogous entanglement monotone in higher dimensions, these universal quantities. Okay, the next point is in a liquid topological order. So by liquid I mean not fracton, so meaning that it doesn't depend on the geometry of space. It's something that you can pour onto a space. In a liquid topological order, the entanglement entropy of a ball of any shape, well, let's say of a region. Okay, no, let me say a ball. Okay, let me just write the formula in 2 plus 1d just so I can be definite, is some non-universal term which depends on let's just say A, depends on the size of the boundary of A. There's an area law term divided again by some cutoff, and then minus gamma, where gamma is a quantity that doesn't depend at all on the shape of A. It doesn't depend on the shape of A, and moreover, Kataev and Preskel and Levin and Wen showed that it's equal to the log of the square root of the total quantum dimension, where this dA's are the quantum dimensions of the anyons, which are the excitations of this topological order. So you see, so A here is some. So in order for this formula to be precisely true, A needs to have just a single boundary. More generally, I guess there's a 0th Betti number of the boundary of A here. And so just from the entanglement entropy of this ball-shaped region, we can extract this data about the anyons. It's not all of the information about the anyons. So there are examples of topological orders which have the same value of this but are different, like toric code and double semyon. But it's something. And yeah, please. Yeah, good. That's correct. So, indeed, maybe. Oh no. Sorry. Actually, this statement is true. So Shuheng is asking about an important subtlety in the relationship between entanglement quantities and the log of the total quantum dimension. The subtlety occurs so the way people usually try to extract this gamma is by adding together combinations of entropies of regions that cancel out the area law term and relate it to a conditional mutual information for some combination of regions. And in that quantity, there can be a spurious contribution, which occurs, where that quantity is bigger than the minimal value. And some people, Bo and Shi and Isaac Kim, and David Lind and some others, Daniel Renard, proved that the actual TE bounds, that quantity is bounded below by the actual TE. Yeah, that's my understanding at the moment. Okay. Another quantity that we can extract just from a ball is the following more involved thing, which is called modular commutator. So far, I just talked about local observables and entanglement entropies, right? Entanglement entropy it's really just one piece of information about the whole density matrix, right? It's just some average over the spectrum. But knowing the density matrix, we actually know quite a bit more. We can define, for any density matrix, we could define the entanglement Hamiltonian K. It's as if it were a Boltzmann distribution. K is not always a local operator. Sometimes it is. But in any case, we can define the modular commutator which, if you like, is the linear response of the entanglement entropy of the region BC to modular flow by the entanglement Hamiltonian of AB. And modular flow just means we treat this as a Hamiltonian. And so you see this is a more refined quantity in the sense that it actually involves the operator structure of the reduced density matrix and not just its spectrum. And one interesting thing about it is this computes. So in a gap topological order in 2+1 dimensions, it computes C minus of 2+1D topological order. It computes the chiral central charge, the number of chiral edge modes going around the boundary, just from the reduced density matrix in some region in the bulk. And I'm not going to prove. Actually, there isn't really a proof of that. But some good evidence for that statement is the following. Well, first of all, JABC is actually chiral. It's equal to minus the thing if you reverse the order, so it matters which way you go around. It breaks parity, which clearly it had better if it's going to measure this quantity. It's under the kinds of assumptions that I'll introduce in just a minute is topological in the sense that it's the same if you deform the regions. You get the same answer. And it stacks. What I mean by that is if I have a state which is a tensor product of two states, which could have their own chiral central charges, then it's additive under stacking. Which is what you do, which is what happens for the chiral central charge. So those are some good pieces of evidence that it's on the right track. And if there's a U1 symmetry, there's a similar formula for the Hall conductivity, which is something like, just replace one of these with the current. So this is a long list of examples of universal quantities that we can extract from a single wave function. And further very strong evidence for the entanglement bootstrap principle comes by taking it seriously and trying to extract more of the universal information. So I guess the last thing I'll say for today is how to make progress using this principle. So an important realization is that if you believe this principle, it means that there should be local conditions things you can study, you can check just knowing the reduced density matrix on a ball that tell you what kind of state your wave function is.
John, I'm going to cut you off sort of right at time this time
Okay.
because of the photo.
Okay, so I have 80 seconds to finish my sentence. Okay.
You also have a whole other lecture.
So generous, thank you. Okay. It implies that there should exist locally checkable, meaning you can compute them just from the reduced density matrix on a ball, conditions that tell us what category we're in. That decide, let's just say that decide the category. So what I mean by category here is the state the ground state of some liquid topological order? Is the state the ground state of a CFT? Is the state a fracton ground state? Is the state some state in the middle of the spectrum of some chaotic Hamiltonian? Right, so these, the wave functions of each of these things is very different, and the tools that you would use to study them are very different. People don't even usually talk about them in the same meeting. But if you believe this principle, then each of these states has some emergent properties that represent its state of matter, either phase of matter or critical state, and we should be able to figure out what they are for each case. And so next time, I'll tell you what the rate locally checkable conditions are for liquid topological order, and we'll explore their consequences a little bit, and then I want to spend some time talking about the analogous locally checkable conditions for 1 + 1 DCFT. Okay.
Ethan, are we good for the photo? Okay, so I'm going to postpone any questions until later, and let's just go get this photo taken so we can still have time to come back and have some coffee before the next session.